Good morning and good afternoon, everyone. I'm Philip Borde, and I will present you the paper entitled Revisiting the Sample Adaptive Offset Post-Filter of the Versatile Video Codec with Neural Networks. This study has been conducted at Interdigital Lab in Rennes, in France, with Franck Galpin, Thierry Dumas, Pavel Nikitin, and myself. The outline of this presentation is the following. First, I will introduce and explain our motivation for this work. Next, I will recap the SAO in-loop post-filter in HEVC and VVC. Then, I will describe the proposed framework and neural network architecture. Next, we will discuss experimental results. And finally, we will conclude and present future perspectives. The in-loop post-filtering has become an essential component in recent video codecs. It allows reducing the coding artifacts and reducing distortion with original samples. H.264 AVC first introduced deblocking filter to attenuate blocking artifacts. Next, HEVC complemented with an additional sample adaptive offset post-filter to soften ringing artifact and color biases. And the recently published VVC standard designed an adaptive loop filter to minimize the mean square error between the original samples and the reconstructed sample using Wiener-based adaptive filter coefficients. VVC improves the compression rate by about 40% compared to HEVC using several new coding tools, but their relative performance may be quite different. For example, the body rate gain provided by SAO and ILF is about 0.1% and 4.3% respectively in ERA for the Luma component with VVC, whereas it was about 2% for SAO with HEVC. At the same time, recent works with convolutional neural networks for image restoration have shown that one can significantly improve the codec performance with neural network-based post-filtering. However, most of the previous work leverage on powerful GPUs platform, and the amount of calculation per pixel is far beyond the capacity and power of current consumer or mobile devices. Both the relative low performance of SAO in VVC and the recent developments in CNN for image restoration have motivated the study of this neural network-based post-filter for improving SAO, targeting relatively small complexity. The concept of SAO is to reduce mean of sample distortion of coding tree units by first classifying the samples into multiple categories with a selected classifier, next obtaining an offset for each category, and then adding the offset to each sample of the category. There are 5 possible classifiers, 4 edge offset and 1 bound offset. The edge offset classifiers classify sample into 5 classes, considering gradient along one of the 4 directions. One correction offset is derived for 4 of the 5 categories. The bound offset classifier classifies sample with their values. Similarly, 4 correction offsets are derived for selected 4 consecutive bands. The classifier choice is made independently for Luma and Chroma samples. Offsets are transmitted for each component, leading to up to 12 offset values per CTU. Our proposed approach is widely inspired from SAO, with a classification operated with a convolutional neural network, which generates a weight map associating a weight to each sample. This empowers much more classes than for SAO, since all different output values of the CNN may be considered as a different class potentially. Similarly to SAO, an offset is derived for each component, so that the weight multiplied by the offset is similar to offset associated to each class, next added to the reconstituted sample. The offset is determined with least square minimization method at the encoder side and transmitted in the bit stream. To add even more flexibility to the proposed scheme, and inspired from the Debarga paper in reference, we provided the framework with the capability to combine the output of two neural networks. Given the similarity of the proposed filter with SAO, and since one has to encode the user network's ID pairs and the offsets for each CTU, the coding of the CTU filter parameters maximally reuse the regular SAO syntax elements, as well as the VTM RDO rate distortion algorithm to choose the best parameters. Our network architecture is very simple. It was chosen to reduce the overall complexity by minimizing the number of operations per pixel, max, and the number of parameters. Then, the convolutional neural networks are composed of a relatively small number of layers, 6, and reduced number of latents per layer, 16 to 32 or 16 to 64. Two versions, V1 and V2, are proposed, V2 being slightly less complex than V1. The training has been made with BVI DVC dataset with video of 4 different sizes, named A, B, C, D, corresponding to 4K, Full HD, 480p or 240p respectively. For our test experiments, we used 16 convolutional neural networks corresponding to different QPs, different modes, and different picture sizes. Many other state-of-art proposals have used several neural networks trained with video coded with different QPs. One motivation of the feature for combining the output of several neural networks was to soften transitions between neural network choice. Our CAO-CNN framework has been implemented in place of the regular SAO in VTM10 software. A module for inferring the CNN models has been developed in C++. The neural network weights obtained from the training stage have been quantized into 16 bits so that all the calculations can be carried out in integers, 16 bits for latent storage and 32 bits for accumulation, with saturation control to avoid overflow. This allows benefiting of SCMD acceleration. Besides speeding up inference, the integer calculation ensures strict bit accuracy between the decoder and encoder reference pictures, so that no drift error occurs in the reconstructed frames, whereas many previous state-of-art work have used floating point. This is a summary of the BD rate gains achieved using V1 or V2 neural network configurations for random access and all-intra, and associated relative encoding and decoding times compared to the regular VTM10 software used as Encore. For our experiments, we used common test conditions defined by the GVET group recently created for studying how the neural network technology may further improve VVC, which is given in the reference below. It can be observed that our proposed approach achieves significant and consistent coding gains on all test sequences and all configurations once integrated into VTM, with an average bit rate gains of 2.8% in random access and 2.4% in all-intra, and about 7% and 5% in chroma in random access and all-intra for V1 architecture. Slightly less gains are obtained with V2 architectures, but with significant reduction in decoding time. The encoder complexity remains below 1.3 times the anchor, and the decoding time for class A is only 6 times the anchor for V2 architecture in random access. In these graphics, we plotted the bit rate gains versus number of MACs and the bit rate gain versus decoding time ratio of our method in orange, and compare with other proposals in the GVET group. The horizontal scale is log. Compared with other proposals, our framework can be considered as a good trade-off compared with the other low complexity methods. Previous works have shown one could generally obtain better results with out-of-loop NN post-processing rather than with in-loop NN post-processing, because the corrected frames are employed as a reference, what is not considered in the current neural network training. Consequently, another improvement could be to retrain neural network for inter using intra-filtered with the neural networks. Also, another option to improve the efficiency of our method could be to reduce the number of neural networks by grouping video sequence classes or QPs at the training stage. Thank you for your attention.